Multiple linear regression, F-test and partial FD test, multi-collinearity, ML, it's a bread and butter, baby, what's your jam?
Greetings, Bio 6611. In this lecture, we're going to introduce multiple linear regression with its motivation, assumptions, and an example. We'll also note towards the end, we'll introduce a modification to the coefficient of determination r squared we discussed with simple linear regression as a value we can use for multiple linear regression, the adjusted r squared. Multiple linear regression can be used to summarize the relationship between our continuous response variable y and multiple explanatory predictor variables x1, x2, up to some arbitrary number xk using linear relationships. Now, this obviously departs from simple linear regression, which only had one predictor, x1. Now, there are many reasons we may wish to include more than one predictor. For example, it may be needed to address the scientific question. We may have issues with potential confounding, which we'll discuss in more detail in a future lecture, or potentially to gain precision. So let's just touch each of those briefly before again addressing some of these in greater detail in future topics on their own. But when addressing the scientific question of interest, it may dictate the inclusion of predictors. For example, the predictors of interest may be multiple scientific factors under investigation, which could also be represented in the case of having a multi-category predictor variable with more than a yes, no, or two category value with multiple dummy variables, or potentially we have to include polynomial terms to address our concerns about the modeling assumptions. There's also the potential for effect modifiers or interaction terms where the magnitude of the effect of the predictor of interest may vary depending on the levels of some other variable as an effect modifier. Now there's also this question as well of confounders we'll discuss in the next slide. Confounders are a variable that affect both the predictor of interest and the outcome of the variable. So for example, we may see that there seems to be this relationship over May to July, where as ice cream sales increase, so do shark attacks. So it would appear that if we could just decrease the sale of ice cream, we might decrease the incidence of shark attacks. Well, in fact, this represents a confounder where the warm weather actually that increases from May to June to July affects both ice cream sales and shark attacks. And so we'll discuss this again in greater detail in a future lecture, but it's another reason we may wish to include a variable in a multiple linear regression model. The final reason is that we may have a precision variable. So this is another role that a predictor can play, where that adjusting for these additional covariates or covariate can change the standard error of the slope estimate corresponding to our specific predictor of interest and make it more precise. Now this occurs when there is a smaller within group variance, but if it increases that standard error, that suggests there's a correlation between the predictor of interest and this covariate or other covariates in the model, which can affect obviously our precision to draw estimates or conclusions based on the confidence interval or p-values. So let's look now at the multiple linear regression model and see how it differs from simple linear regression. So we're actually going to see that for the most part it's very similar and we're just expanding out our knowledge. So as with simple linear regression, we're going to assume that our outcome y conditioned on our x's, now in this case it's more than one, it's 1 up to k, will still be normally distributed, where we'll have a mean of y given our x's and the variance of sigma squared y given our x's. Now note here that we are trying to use this bold term for our x's to represent a vector of multiple x values instead of writing out that x1 through xk every single time. Unlike before with just a single value though, we are now assuming that the underlying center of our distribution will change linear based on several other factors. So again, instead of just focusing on beta 1 x1, we're actually going to account for x2, x3 up to xk. Or equivalently, we can write this as well with the error term, our random error, which we also still assume is distributed normally with mean 0 and variance sigma squared y given x. Let's discuss how the interpretation of the coefficients is quite similar to simple linear regression, but does have a few little nuances to keep in mind. For example, the intercept. Theta naught is going to now represent the expected value of y when all of the other predictors, not just x1, are equal to 0. So again, very similar to before, where it's really that estimated mean when everything else in the model is set to 0 or false if it's a dummy variable. But in this case, all of those variables have to be set equal to their 0 state. The slope likewise is quite similar, where beta j, any one of our slope parameters, is the expected change in y associated with a 1 unit change in the corresponding predictor xj. However, we have this additional detail that we assume all the other predictors are held constant. Now we see this below that, for example, if we're interested in a change in 1 unit in x1 for an increase, so we see here that we're saying y given x1 equals x plus 1 versus x1 equals just x. Well, if everything else is held constant, we can see that b2 is times c2, beta k is times ck, and we see that when we actually then have the x plus 1, it's similar when we just use x, so we have beta 2 c2, beta k ck. So therefore, the difference is still just beta 1 is that 1 unit increase, but it does have this important fact that we have to use the exact same held constant values for the other betas. We can also note that we can use least square estimation for our multiple linear regression parameters. As before, we will use the data of our outcome yi and all the predictors for each person, x1 up to xk, to derive estimates for beta naught through beta k. This model will then represent the same thing we saw before, simple linear regression, just with additional beta and x terms, where y hat will equal beta naught hat plus beta 1 hat x1 plus yada 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 up to beta k hat plus xk. The differences between our fitted values and the observed values will still be known as the residuals, where we'll still estimate it the same way, where we take our observed y minus our predicted y. Here, though, again, the predicted y is based on our multiple linear regression model instead of the simple linear regression model, and we'll still use the same approach to minimize the residual sum of squares, also known as our error sum of squares, to derive these estimates. Now let's discuss the assumptions for multiple linear regression. And it turns out they're actually the exact same as we have for simple linear regression, with the caveat that we're now considering multiple predictors. For instance, we have existence. For each combination of values of the predictors x1 up to xk, y will be that random variable with a certain probability distribution which has a finite mean and variance. We also assume that there's linearity of y for each specific combination of our x values, independence of all of our observations still. There's the assumption of equal variance across all of the fixed combinations of our multiple predictors, x1 through xk. And we also still assume normality, that for any fixed combination of x1 through xk, our residuals will be normally distributed. And again, this assumption is primarily used to do hypothesis testing and construct our confidence intervals. So now that we've seen actually multiple linear regression is fairly similar to simple linear regression, just with additional predictor terms, let's walk through an example starting with simple linear regression. So with our Rosner FEV smoking data set, let's say we're interested in the effect of smoking on FEV. So before, with the tools we developed so far in 6611, we could really only naively fit a simple linear regression model with smoking status as our only predictor. Now, if we do this, we see our results down below that we have our estimate that the smokers actually have a higher FEV by 0.71 liters on average than non-smokers. So if we graphically represent our data and what this fitted regression model looks like, we see we have this fitted regression line where the predicted FEV equals our intercept of 2.57, the predicted FEV for a non-smoker. And then we have plus 0.71, that's our blue line here in the figure that has this slope that's slightly positive for a smoker. In other words, our interpretation is that there is an expected FEV increase of 0.71 for smokers compared to non-smokers, and that smokers actually have better lung function than non-smokers. And it's quite significant. Now, if we stopped here, we would draw some likely erroneous conclusions, and maybe back in the heydays before we had more robust scientific and public health research, might be concluding that smoking is healthy for you or good for you. Well, in fact, we now know this doesn't clinically make sense. It seems like there's likely something else at play here. For instance, maybe we realize in our dataset, because it is 3 to 19-year-olds, that smokers tend to be older in our dataset than non-smokers, and that older children tend to have a higher FEV than younger children just by nature of growing up, growing larger, and having your lung capacity increase. Thus, we think age actually might have the potential in this model to be a confounder. So we decide that we want to somehow control for age in our analysis. So we have a new question at hand here, that for a group of children at a given age, do smokers have a lower FEV compared to non-smokers, or conditional on age? Is there a difference between smokers and non-smokers? Now, we have two options at this point actually. Option one relies on methods we've discussed so far in class. In other words, we could do a stratified analysis, breaking up the ages into different subgroups, and maybe do things like t-tests, Mann-Whitney U-test, or some form of permutation test comparing the FEV within each age strata. Now this requires, of course, that we break the age up from its continuous version of a predictor variable into a categorical one, therefore losing some potentially meaningful information. Option two would be to actually expand our knowledge that we're discussing here to use a multiple linear regression model, which can get a single average estimate of the effect on smoking for FEV, while adjusting for differences that might be caused or associated with age. We'll start just by looking at the stratified analysis to see why it might be suboptimal. So the first thing to note is that, well, I guess, fortunately, if we break it up here, the 3 to 8-year-old age group has no smokers. So they're all non-smokers, which is good news. The downside there, though, is that we actually can't do any comparison within that age group then, because it's only non-smokers. We then see by breaking up the following age groups into 9 to 10, 11 to 12, and so forth, we still have small numbers of smokers compared to larger numbers of non-smokers in most age groups, but also that our sample sizes tend to be somewhat smaller towards the upper end of our age range. Therefore, what we see here by comparing a t-statistic and a p-value from a two-sample t-test is that actually we have no significant difference between smokers and non-smokers within strata, which still may seem a little strange that we expect the effect of smoking to potentially lower one's FEV. And in fact, if we plot sort of this point estimate value here we see on the figure above, the orange dashed line is the mean of smokers. And we do see that as it tends to get older, besides some noise, it does seem to be lower than the sort of mean that might be there for non-smokers. So let's see what option 2 looks like by now adding not just smoking status, but plus age to our multiple linear regression model now. And we see here the output looks quite similar to before, but the big difference is that instead of just one parameter that's not the intercept for smoker, we actually also have another estimate for age. So in this case, if we take those values from before, we can write out our fitted regression line. The predicted FEV is going to equal that 0.37 intercept plus 0.23 for the slope of age minus 0.21 for the effect of smoker. So our interpretation now makes more clinical sense. On average, FEV is 0.21 liters lower in smokers compared to non-smokers when age is held constant. Thus, we conclude that smokers actually have worse lung function compared to non-smokers of the same age. And because we're leveraging the entire data set, we have more statistical power to detect that difference, unlike in the stratified analysis. We can actually say that p is less than 0.05. Now, a few things we can note on this figure here. We have plotted the means that are not adjusted for FEV for the age status, and we see that here is our difference for that simple linear regression model from before of 0.71, where smokers have a higher mean. We now see, though, that when we take this information and we actually look at adjusting for age, we see that that's where we have that negative 0.21 beta coefficient, where smokers have a lower predicted FEV. So as a preview of things to come, we can also note that the effect of age on FEV is assumed to be the same for smokers and non-smokers. Now, we can imagine that actually as age varies over time and how long you've been smoking, there may actually be some form of interaction between these two, so it's not actually a constant linear effect. We can relax that assumption that we have in the current multiple linear regression model by including what we term interaction or effect modification terms. And we'll discuss those in their own lecture later on. So to wrap up this lecture, we just want to also note another modification when transitioning from simple to multiple linear regression, and that's looking at how we can tweak our coefficient of determination, r squared. So remember, r squared, that coefficient of determination, is calculated as the ratio of the sums of square for our model over the sums of square total. And this gives us the proportion of variance of y that can be explained by our predictor, or in our case here, predictors in multiple linear regression. However, when we add more explanatory variables to the model, this definition of r squared will always automatically increase or at least stay the same. Therefore, we can't really use r squared to compare models with differing numbers of predictors, because it will always look better to use a larger and larger model if we're simply trying to maximize our r squared. This can be addressed with a simple modification by introducing the adjusted r squared. In this case, we account for the sample size and the number of terms in the model, where we see we have this adjustment factor here, as well as a 1 minus 1 minus r squared term. And we can note in this formulation, r squared adjusted can actually be negative, and in fact, it will always be less than or equal to r squared. Further, it will only increase when the increase in r squared is more than we would expect to see by chance. So in other words, is there an actual meaningful contribution of adding this variable or variables? So for these reasons, using r squared adjusted is actually more appropriate to evaluate the model fit in multiple linear regression when we have these multiple predictors. So just in closing, MLR, or multiple linear regression, allows us to investigate multiple predictors of interest, and they can serve different roles, such as being a confounder, an effect modifier, or to improve precision of our predictors. We have the same assumptions as we had for simple linear regression, and the coefficient estimates are obtained in the same way with just a couple extra steps we have mathematically for having multiple predictors. We explored an example where, by controlling for age, the potential confounder, we changed our conclusion about our simple linear regression results of the effect of FEV and smoking status. And further, we noted that the adjusted r squared, which is interpreted the same way as just the r squared, gives us a little more information about the amount of variability explained by a model, while accounting or adjusting for the fact we have multiple explanatory variables. And so with this start to our multiple linear regression career, we'll move forward to see other examples and different things we can do with this model to address more complex questions of interest.